Hi everyone, in this video for 163.14 Combinatorics we're going to look at classifying. So we're going to look at the number of ways to classify some objects, and we're going to see that the answer is given by some multinomial coefficients. And this will let us answer these first two questions, and then we'll need to extend the idea that we use in order to answer this third one. Okay, so this first question says I'm travelling in Italy, we're sending postcards home again. We want to send a postcard home to each of 10 friends. Okay, and this time the post office just sells 3 different postcards, and I buy 3 of the first card, 5 of the second, and 2 of the third. And so how many ways are there to send them to my friends? Okay, well let's say that the postcards are of say the castle, the square, and the fountain. And I got 3 of the castle, 5 of the square. That wasn't very imaginative to me. I should have got 5 of the castle really, and so 2 of the fountain. So what I want to do is I want to essentially classify each of my friends as either being sort of the castle, the square, or the fountain. So maybe I decide to send Adam one of the square, Bella the fountain, and also send Carl the square. Tiva loves castle, so I send her the castle, and then perhaps I send that to Eva as well. And so I want to classify each of my friends into one of these 3 types, either the castle, the square, or the fountain. And when I do that, I want to make sure that I've got 3 friends classified as the castle, 3 classified as the square, and just 2 classified as the fountain. Okay, so that's sort of the framework. So let's see how to do that. So it says, here's our theorem. So it says let S be a set of size n, and let's suppose that k1 plus k2 plus ... plus kr is equal to n. And the number of ways to classify the elements of S into R types so that there are ki elements of the ith type is given by the multinomial coefficient n, choose k1, k2 up to kr, and that's equal to n factorial of k1 factorial, k2 factorial, ... up to kr factorial. Okay, so in the problem, I guess in problem 1, we've got, so n is equal to 10, right? So that's our 10 friends. They're the things that we want to classify. R is equal to 3. That's the types of the number of different types, and that's the 3 postcards, other types. And so k1 is equal to was 3, k2 was equal to 5, and k3 was equal to 2, and 3 plus 5 plus 2 is equal to 10. Okay, so that's how our first problem fits into this theorem. Okay, and so then let's look at the answer in a moment. Let's sort of see why this is true. But I guess before we do that, so you might say this looks kind of familiar. Haven't I seen something a bit like that before? And then you have, because the binomial coefficient is a special case of this, where k1 is equal to k, and k2 is equal to n minus k. So just in this binomial coefficient case, so I guess we said this was the number of ways to choose k objects from n. So k is the k that we choose are selected, and the other n minus k are classified as unselected. Okay, so this binomial coefficient is classifying n things into 2 types, selected and unselected, and we want to choose, there's going to be k of the first type and n minus k of the second, and again k plus the n minus k adds up to n, right? So the binomial coefficient is just a special case of this theorem right here. And so we can prove it in the same way that we did the binomial coefficient. Right, so we're going to write down n boxes. We're going to write them down in blocks. So I'm going to have k1 boxes, and then I'll have k2 boxes, and then eventually at the end I'll have kr boxes. Okay, and altogether I've got n boxes. Okay, and so I'm going to do the same thing. I'm just going to write all of my n objects down in these boxes in some order. Okay, so there's n factorial ways to fill the boxes. Alright, so that's the n factorial orders in which we can fill these boxes. And then everyone that ends up in one of these first k1 boxes, that's going to be the type 1. So these are all going to be type 1, type 2, up to type R. And so then the question is, how many ways to get the same outcome? So how many ways give us the same classification? Well, to get the same classification, so any way of writing these ones, these boxes, so filling these boxes, any way of sort of scrambling the k1 things that I put in here is going to give me the same choice of what is type 1. Okay, and then so there's k1 factorial ways to reorder the things that we put in these first boxes. Okay, and that'll all give us those will all give us the same choice of classification of what is type 1. Okay, and then there's k2 factorial ways to scramble the things that we put in these boxes. So 1 multiplied by k2 factorial, and so on up to kr factorial. So that's the number of ways that I can scramble the things that I put in here. So in order to get the same choice of classification, so I want to count the number of orders that give me that same outcome. So any choice I've got, so it's a multiplication principle again, and we're going to make we've got R choices, and at the first step we've got k1 factorial ways in which we can choose to fill in these boxes. At the second step we've got k2 factorial ways in which we can choose to fill in these boxes, and so on up to kr factorial ways in which we can fill in these boxes in order to get that same classification. Okay, so this is the number of ways we could go about filling in these boxes that give us that same classification. So each classification occurs this many times, and so we need to divide this n factorial by this in order to figure out the number of possible classifications. Okay, so that's where this theorem comes from. So let's apply that. Go back to the problems. So we said n was equal to 10, r was equal to 3, k1 was equal to 3, k2 was equal to 5, and k3 was equal to 2. Okay, and so the answer is going to be 10 factorial over 3 factorial, 5 factorial, 2 factorial. Okay, so that's the answer to the first question. Okay, alright, so the second question is, how many ways are there to rearrange the letters of the word contentment? So this is a classification problem too. So we've got, I guess let's think of, let's say the numbers 1 to 2 up to 11. It's 11 because I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've got 11 letters. So basically I'm trying to count anagrams of contentment, right? And so I want to classify 1 to 11 into the type CONT, E, and M. Did I list everything here? Hopefully. So let's say, I should have prepared an anagram actually, never mind. Well, when I say anagram, I'm not talking about words that make sense actually. We want to talk about different orders that we could put these letters in. Okay, basically I want to classify each 1 to 11 as one of these letters. So let's just count how many we've got of each letter. I've got one C, I've got one O, I've got 1, 2, 3 N's, T, there's also 3 of those, E, there's 2, and then finally M is the last one, just one of those, and so that adds up to 5 plus 6 gives me 11. Okay, so I want to classify the numbers 1 to 11 into the type C, O, N, T, E, and M in such a way that there's one C, one O, three N's, 3 T's, 2 E's, and 1 M. Okay, and then if I classify 1 as N, then that's going to be my first letter. If I then classify 2 as E, that's going to be my second letter. If I classify, and so on. So that's how we sort of turn this into a classification problem. Okay, so here our N is equal to 11, R is equal to 6 because I've got 6 different types of letters. K1 is 1, K2 is also 1, K2, 3, sorry, is 3, K4 is also 3, K5 is 2, and K6 is 1. Okay, so the answer is going to be 11 factorial over 1 factorial, 1 factorial, 3 factorial, 3 factorial, 2 factorial, 1 factorial. And we can just leave out the 1 factorials because they're equal to 1. And so this is 11 factorial over 3 factorial, 3 factorial, 2 factorial. Okay, so there's our answer. Okay, so our last problem is a little bit different. It's a bit of a classification problem, but then we're going to need another idea at the end. But it's not really a new idea, it's just an idea that we've already used. Okay, so here we've got a class of 8 children, and it's to be divided into 5 unlabeled groups, so that there are 3 groups of size 4 and 2 groups of size 3. So how many ways are there to do this? Well, the reason this is a little bit like a classification problem is that we've got 5 types, right? So we've got groups 1 up to 5, and we're going to have 3 groups of size 4, so these are all size 4, and then these ones are size 3. Okay, so we could think of it as a classification problem where we're classifying these 18 children. That was supposed to be 18. Whoops. We're taking the 18 children and we're classifying them into these 5 groups to get them to, say, work on some project together in their groups. And so there's going to be 4 of the first type, 4 of the second type, and so on. But it says the groups are unlabeled, so we can't actually say which is the first group and which is the second, which is the third. So there's just going to be 4 groups of size 4, oops, and 2 groups of size 3. Okay, and we can't say which of these is the first and which of these are the first, second, and third, right? So if I let's sort of take the same idea of filling in our boxes. So we'll have 4 boxes, and then a line, and then 4 boxes, and so on. And at the very end, we'll have boxes of size 3. Right, and so I've got 3 blocks of size 4, and at the end I've got 2 blocks of size 3. Okay, and so we're going to fill in these boxes with the children, all right, and then essentially we get 18 factorial over 4 factorial cubed times 3 factorial squared. Okay, so that's sort of the number of ways to fill these in, so that we'll classify them into groups 1, 2, 3, 4, and 5. But then, because we can't tell which of the 2 groups they're unlabeled, so we can't say which of these last 2 groups is group 4 and which is group 5. If I swap the order of these 2 groups, I get the same division of the children into groups. And likewise, if I take, it's a bit lazy of me really, I could have just drawn in those other boxes there, right? So these are my 3 boxes of size 4. Right, if I reorder these blocks here, so I'm just going to scramble those 4 in their blocks. There's 3 factorial ways in which I can order these blocks here. Okay, and that's going to give me the same division of the children into groups. So because the groups aren't labeled, we actually need to divide by that 3 factorial times 2 factorial, which accounts for the number of ways once we sort of take away the labels. So this was the answer we get if we label the groups as 1 to 5, and then if we take away the labels, then we need to divide by this to account for that. Okay, and so that's our final answer there. Okay, all right, leave that there.